All right, good morning. I'm planning to do the contest that I missed from last Saturday and screen share it. So it was, yesterday, contest 278. So here we go. All right. Open these guys up. Keep multiplying found values by 2. Multiply by 2. Otherwise, stop the process. Original is 3. Output's 24. 3 is found. So multiply by 2, we get 6. 6 is found. 12. 24 is not found. Okay. Alrighty. A x while, let's do this. Scene equals set A while x in scene. X times equals 2, return x. Does that work? Yay. All right. All divisions with highest score of binary array. Okay, so I just skimmed through this. I'm going to read through it a little bit more detail and then look at the example. So all divisions with highest score of binary array. 0 index array. All right, divided at index I, where I is n inclusive. Num sub left and num sub right. Num sub left has all the values of num between 0 and I minus 1 inclusive. So 0 to I non-inclusive, while num sub right, okay, is I inclusive to n minus 1 inclusive. Okay. Okay, so it's 0 to I non-inclusive and I to n non-inclusive are the two, the left and the right. Okay, so I is 0. If I is 0, then left is empty. Okay, that makes sense. And then if I is in, then right is empty. Okay. The division score is the sum of the number of zeros and the number of ones. Okay, zeros in left, ones in there. Okay. Okay, so we should be able to just do a sliding window and then some pre-calculations, I think, and then that should be fine for a linear algorithm. So not TLE. Number of zeros on the left, number of ones on the right. Right, okay, cool. Okay, so let's see, we'll call this guy, X will be our score. Or I don't know, whatever, we can call this, and just call it score. For X and A, right, for each value, okay, hold on, actually okay, I have to come up with an algorithm, right? So do the pre-calculations for O of 1, lookups during linear scan of A, right? Okay, so N is the length of A, and then we'll do L. L will just be the count of zeros to the left, and it'll be ongoing sum from left to right, and then R will be the number of ones from right to left, right? So okay, so this would be 0 times n, and R likewise will be the same thing. 0 times n. I wonder if we can do this actually. Something like that. Okay, and then for I in range n, 1 to n. Actually, we want to make a copy of A, right? because it's the zeros and ones that are going to add on to themselves. Yeah. Okay. So let's just do this. Make a copy of A, and then for I is 1 to n, I say L sub I. I want the zeros to be ones and ones to count as zeros. So actually, no, I'll just keep it easy on myself. Let's just do, let's go back to this. Times n, 0 times n. Okay, so L sub I, L sub 0 equals 1 if A sub 0 equals 0. Else, oh, actually, I should do this. A sub 0 XOR 1. Right, so we can flip that bit. Similarly, when we build up the right recurrence relation, right will be A sub n minus 1. So okay, this is counting zeros, this is counting ones. All right, and then plus equals L sub I equals 1, or actually let's do A sub I XOR 1. Okay, so L sub I will be the opposite of 1. So if it's a 0, it'll count as 1. If it's a 1, it'll count as 0. And then L sub, let's do that, and then plus L sub I minus 1, right, the previous one. And for right, we do the same thing. For I in range n minus 2 down to -1 non-inclusive, R sub I equals A sub I plus R sub I plus 1. Okay, and then the score will be all those things to the left and plus all the things to the right, right? I wonder num sub 0 for left is actually, oh yeah, it's not inclusive, right? It's not inclusive of I. So L sub I is A sub previous one, right? So it's not plus L sub I minus 1. So this is non-inclusive, so this is always 0. Similarly, right is non-inclusive, so that's always 0. Right, so I don't want to offset them because that's kind of a pain. A sub I minus 1. So if A is 1, 1, A equals, right, 1, 1. Index 0, 1, and 2. Then what does L and R look like, right? So L initially is this, R initially is this, and then we're going to say to the left of 0, there's nothing exists there. So we never want to count that. And to the right of 2, nothing ever exists over there. So we can do a linear scan from 1 to n minus 2 inclusive. 1 to n minus 2 inclusive. So 0, so 1 left to be 1. So left will be 1 here, and then oops, right will be 1 there. I'm surprised. Left. I'm surprised at 1. I'm surprised. Oh, right is inclusive. Okay, that is inclusive of that. Left is 0. Right is You add it one more time because you go off the end. Okay, so I think it does make sense to append sentinel values onto the left and the right at the end after I build up what it is I want to build up, I think. Yeah, so remember left is whatever is from 0 I minus 1, right? So 0 to I non-inclusive. And then similarly right is from I inclusive to n minus 1. Right, so it's I to n non-inclusive. So as long as I can line this thing up, it should work out without making it too complicated and confusing myself, hopefully. All right. Okay, so let's put a 1 on the left and a 0 on the right, and then do the same thing, right? Okay, let's make this easier on myself, right? Here, let's make this easier on myself. Basically, I want to append, this is the input array A, equals this, then calculate my L and R, right? Based on sticking a 0, 1 here and a 0 there, right? Okay, so if I stick a 1 there, I don't count it for left, and if I stick a 0 there, I don't count for the right. And I think that will work. Right, so non-inclusive, inclusive, think so. Okay, let's do this. A equals 1 plus A plus 0. Right, so concatenate those, get the length of it, fill in these guys. So L is non-inclusive. So we're flipping the bit and adding L minus 1 from 1 to n, and then we can formulate the score for I in range from 1 to n minus 1 non-inclusive. Score plus equals L sub I plus R sub I. Something like that. Whoa. 8 is not a valid range. What is going on? List integer. Oh, list of integers. Only index 3. That's the highest possible division. Oh, we're keeping track of the highest scores. I see. Okay, not the total score. Okay. All right, let's do this. Use a map to keep track of our best score. Candidate is L sub I plus R sub I. If best is less than candidate, then best equals candidate, and then M will be a default, let's do this, default dictionary of integers, or no, list. Let's do this, a list, right? So m sub best append I, and then we'll return m sub best if it's less than or equal to. Wait, that should work. 3, that is not right. Oh, dang, okay. Uh-oh. Well, I guess I can output what the score is at each of these. 0, 1, 2, 3, and then 4. Oh, do that fourth one to count the last one more time. Okay, well, let's just print this out and see what's going on. We'll debug it. Print out what my candidate is. All right, so the ith candidate. L sub I is L sub I, and then R sub I is R sub I. Bear with me as I debug this. It might be a little bit. Okay, so is this right? Candidate is 1, 2, 3, 2, and then I don't have that last one. So, oh, that is right, but my index is off by 1. Okay, remember I offset it by 1. And then I didn't do that last one. Let's do to n. Okay, that looks right. 2, 4, 0, 0, 0 is 3, and then that's 0. Okay, let's see. Custom, use example. That looks right. Okay, this looks legit. Thinking. Well, it sure is taking a long time. Yay! I was a little concerned it's going to TLE there for a second. All right, that's cool. It's a decent solution too. All right, find grid with given hash value, or find substring. Okay, read the problem. I need more coffee. Okay, so we got some hash function. Okay, val s sub I is the index s of s sub I in the alphabet. Already. Okay, so I'm looking for a substring with this hash value of size 2. So we should be able to do a sliding window of size k, just look for the hash value. The hash of fbx can be compared to the hash of fbx. bxz. fbx is the first substring of length 3. It also has it, but appears later. Okay, so we want the leftmost substring, right? The first occurrence. Power modulo is 1 billion. 20,000. Okay, I kind of skimmed through. I'm going to read through it one more time so I can get this actual function understood, and then I'll start implementing it. Okay, so given P and Q, or P and M, string, so each value of each character in the string multiplied by P and all that modded by M. Since these things are pretty huge, I'll probably want to mod it as I go. So when we do the sliding window, we'll basically drop off the left and add on to the right. So that'll be my game plan, right? Sliding window of size K. So first I'll initialize the window to the first K hash values, then slide window interval I, j. Basically drop I, add j, see if hash value target t is acquired, and then if so, return the string, right? Return string, okie dokie. That's the game plan. This guy's P, this guy's M, and this is our target hash value. Alrighty, so it's each value of A is 1 through 26. Okay. Should be fine then. The ordinal value. The ordinal value of lowercase alphabet is 97 to 122 inclusive. So let's do this. Const equals lambda some character, right? So do ordinal value of that character minus 97 plus 1. So it's a 1 based offset. So then the hash function f equals, given the index I, will return cost of s sub I. Right, so look up that value. And then multiply it by the power and mod it by M. F sub I. Let's just do this. Let's call this thing hash. Ooh, I don't know. Maybe we can call this whole thing cost, whatever. This is fine, right? Cost of that is ordinal value of the ASCII character minus A to offset it, 1. So this thing times P modulus M. Fine. Okay, so our total cost will be the sum of all costs I for I in range K. So 0 to K minus 1 inclusive is the first K. If, okay, so while T does not equal T, then we'll drop I, add J, and then cost of I. Okay, so I equals 0, J equals K. That's our sliding window. And then we'll end up returning S sub I to J, right? So if it's that first one, return that slice. Okay. So we need to drop I here and increment J. Let's do this. Cost. Okay, yeah, that's cool. t minus equals cost of I, t plus equals, let's see, is it guaranteed to have an answer? Okay, yeah. Cost plus equals cost of j. And then increment I and j. Something like that. Let's see what happens. Uh-oh, runtime error. String index out of bounds. Uh-oh. S sub I. Leetcode should do the double E of size K. Five times one, 5 times 7? Wait, what do you? Oh, p to the power of 0. Or is that p to the power of 0? P to the power of 1? P to the power of 0? 7 to the power of 0 is 1. 7 to the power of 1 is 1. Okay. So my cost function is not correct. Oh, okay. So that makes it a little bit more difficult. So as we shift, we have to divide by the power as well. Divide each of those by the power. Yeah, so this is not quite as trivial as I thought. So that's where the quadratic, okay. Quadratic brute. I guess quadratic solution is naive, right? Let's do that first. Let's start there. Get a working solution and then optimize. So the difficulty here is calculating the cost, right? So each power shifted, right? So divide each of those by power as you shift. Each sum times the power. Okay, I think I'm trying to skip a few heads. All right, currently, oops. I'm trying to take too many steps and confusing myself, right? Okay, so just take next step. Next step is the brute force, right? Just do the easy way first. Times p to the power of whatever it is gonna be. Right, cost. Okay, so to do optimize this part to avoid going back. So this seems like to imply DP, right? Remember in the past to formulate the future. Okay, so sliding window, this will be brute force naive solution goes back, right? Goes back in time to retrieve previously seen values or recalculate previously seen values as the window slides. All right, so we slide this thing to the right. Come on, where's this? This thing to the right. All right, hold on one second. I'm gonna go grab some more coffee. Okay, got a fresh cup of coffee here. Ready to go again. Okay, where was I? All right. Well, the total isn't the target total, right? We're gonna go back, recalculate our powers of P for the hash as we go. So simple, naive quadratic solution of n squared will TLE, but at least it's correct if I do it right. So okay, let's do this. Talk is cheap. Let's get to it rather than get stuck in the analysis paralysis here. Okay. So basically, T doesn't equal T. Okay, so I can make this cost can be just a function, right? So def f, the cost of starting at I and going to I plus K non-inclusive, right? So from I to I plus K non-inclusive. T will initially equal 0, and we'll return T will be our total sum. Okay, so T plus equals the ordinal value at S of I. Let's see, hold on. While I is less than I plus K, right? I want to increment I, oh wait, while, okay, let's do J equals I plus K, right? And then while I is less than J. There we go. Do this. So last endpoint. Okay, so the ordinal value there, offset it by the ordinal value of A, which is 97 at 1, so it's 1 based value. Right. I don't know. We call this thing G. It doesn't matter. G equals lambda I. Just turn that thing. G of I multiplied by P to the power of oh, okay. Let's do this. J is 0. Well, I plus J is less than, or no, or J is less than K. All right, J is less than K. Increment J. We'll bring it to the power of J, right? P to the power of J. P to the power of J. I think that works, right? ASCII ordinal value times P to the power of J mod M modulus. Call this thing mod. Mod school. All right, M is fine. I'm not using a map, right? It's just cool, whatever. Okay, so ASCII ordinal value multiplied by the power of P to the J, just incremented as this thing slides. T plus equals that, right? That looks good. I don't need J in this case, right? T is then F sub 0. T equals F sub I. So I plus equals 1. T equals F sub I. Right, so this should be the naive solution, I and then I plus K, since K is non-inclusive. Okay, let's see what happens. TC, okay, that's a little bit off. That's a little off, okay. Let's see if this calculation's right. So EE is what I want. I can just print out the hash value. So 5 times 1, which is p to the power of 0, p to the power of 1, 20, 40 mod 20 is 0. Mod plus equals. So the whole sum modulus equals, okay. Modulus m, and then t modulus equals m at the end. Okay. T modulus m. All right, let's print this out. Debug it, bear with me. So f sub 0 is our current total. I'll just do t, I guess. Let's see. I is 0. T is total. Hold on, I gotta sneeze. Oh, I thought I got to sneeze. Okay, anyhow, let's do this. Print out I and our total. And then let's do this. Let's print within our function I. We're going to consider slice. Oops. Consider the slice as sub I to I plus k. Consider this. It's going to be that. And yeah, let's just print an extra one here. Okay, let's see what happens. Consider slice LE, consider slice EE. Oh, okay. What did I do? Why was it returning? Oh, maybe it's this part. I don't know what I did. Okay, I think it's that part. Let's try the other test case. It looks like it's legit. It looks like it's correct, at least for a brute force solution. Your answer is EE. And then what about, oh yeah, run it again. EE and XZA. XZA is not right. Computed this way. 32. BXZ is 86. XZA is 32. So BXZ is not calculated correctly. BXZ, FBX, BXZ. Okay. So FBX is 58, whereas it should be 32. Okay, let's do this. An additional debugging. G sub I is the ordinal value. Oh, it's G sub I. Oh, that's why. It should be G sub I plus J. I plus J. Right, I is where we're at, and J is the offset. Okay, so I was adding the wrong thing. Okay, let's see if this is right. FBX LE this time is not right. Total is 7 for LE. What's the ASCII order value of L? E is 5. Hold on one sec. Do my idle thing here. All right, what is the ordinal value of L? 108. 108 plus 35, 143. 143 modulus 20. So basically divided by 20, what's left over is 3, right? Is it 0? Or 7? Right, it's saying it's 7. Something's not right. All right, we're considering LE. G sub I plus J, power of P to the J, modulus M. Yeah, I don't know. All right, let's just do some debugging, see what happens. G sub I plus J is G sub I plus J. Power of P to the J is pow P to the J. Print. Return T modulus M. How is it that this thing's changing? It's like I'm printing out the debug message and now like the code is different. Did I really change something or I just not run it? Like what the heck? Here, comment these things out. I don't know. Maybe I haven't had enough of coffee, but this looks legit. EE and FBX. Okay, so this should TLE, right? This is basically what I'm saying is this is a brute force quadratic solution. This is the easy solution. And then I need to optimize this so it doesn't TLE. Let's get rid of these debug prints here real quick. Submit, okay, this is expected to TLE. Expect TLE. And we'll work on optimization next. Okay, it should run for a while. Okay, there we go. Time limit exceeded as expected. I don't know how helpful this thing is. I don't know. I mean, it's kind of cool. I don't have to wrap it in prints, multiply it like that. The cost of it is you have to go look it up somewhere else, though. Oop. Let's just do this. I plus J, ordinal value of that, offset by A. All right, so this thing will TLE. It's not a valid type. Oh, okay. Oh, excuse me. Too many new lines. Okay, so this is the correct solution, but it's too slow. Okay, so now the question is, how to speed up this calculation, right? And I'm pretty sure this is like we need to use the past to formulate the future, right? In a non-naive way, right? Basically, I'm going back every single time and calculating it from I to k non-inclusive, or I to I cos k non-inclusive. Let me not go back and calculate this again. It's that power thing, the power of the j. This times that to the j, and you have to go recompute them all because the power of the j offsets everything. Each of these things. I don't know. I feel like I've spent a lot of time on this. I need to maybe take a break and then come back. I'm a little worn out. I don't know if I want to go back and do this. These are pretty basic. And they're helpful, I guess. Just for practice. Oh, X is in the scene. Shift it right. Yeah. This seems like a decent solution, right? Set. Their set will be integers. Yeah, so I'll just build up a little bit of confidence and just check out these here real quick. All right. X. Set scene is a while scene dot find x equal dot n x multiplied by 2. All right. C++ solution. Python 3. Let's do JavaScript. We'll do our Kotlin as well. Oh. All right, here we go. Let's code this up here real quick. Scene is new set A. I'm wondering if there's a way I can shorthand this so it's like a one-liner. That'd be cool. I wonder if I can do this. Just return x at the end after we do this. So while scene has x multiplied by 2. Oh, let's see. While it doesn't like that unexpected token while. Yeah. Okay, whatever. Let's do this and then return x. It's still a pretty short solution. That's right? 24. Yeah. All right. Kotlin. Okay, so Kotlin, I'm not going to be able to change that. So var x is x underscore. We'll turn that while our scene equals a.toSet while scene contains x equals x shifted left by 1. Looks good. Yay. Alrighty. Use a set, I guess, check scene values of the input array A. And multiply x by 2. The value has been seen. Yeah, whatever, this is right. Let's just multiply each value x, or multiply the original input value x by 2 while x has been seen. Yeah, something like that is fine, right? Nothing too fancy. Do solutions, boom. Multiply the original input value x by 2 while x has been seen in the input array. Okay. All right. That's cool. All right, nice little confidence booster. I'll take what I can get. You know, this one was kind of tricky. I can go back and solve this one again. Yeah, it's just kind of tricky. Just like where the left and right start and stuff, just to be careful. Let's just code this real quick. It's good practice. And then if I have time, I'll go back and give that other one a shot. And I haven't even looked at Q4 yet. So maybe Q4 is easier than Q3. I don't know. I'll eventually look at them all though. Okay, so you wanna see, let's do this. If we're gonna push stuff over the left-hand side of this thing, we better use a deck. Binary array, let's just call this thing nums for now. A will be our deck. Deck A is nums. Okay, and then A dot push front. We want to push 1 to the front and a 0 to the back. Push front, push back. All right, and then we'll keep a copy of those. Or no, I do the pre-calculations for L1 lookups as I do the linear scan, right? And then I'll need a map, keep a track of each of those things. Right, using a map for our best, map, best, and then that'll be a list of the indices. Let's do this, then return map. Oop, hold on. Map equals that thing, map m, return m's best. L is going to be an array length n equals zeta size. It'll be length n. It'll all be zeros. And similarly, R is of length n, all be zeros. And for 1 to n non-inclusive, we'll build up L upon itself. L sub I equals L sub I minus 1 plus A sub I minus 1 XOR 1, right? So flip the bit on that thing. So I non-inclusive. And then R is also I non-inclusive in the other direction, right, from right to left. So R sub I on the right of it plus A sub I. So if it's a 1, then it counts, right? That looks legit. Then calculate all our candidates, find the best, and push that. One to n. So our candidate value is L sub I, R sub I. And then if best is less than or equal to candidate, then we'll say best equals to candidate, and then m sub best dot push back I minus 1, right? So it's 0 based offset. Since I 1 based offsetted it here, I think that looks right. Okay, let's see what happens. 3, 0, 2, and 2. That is not right. Okay, so what happened? Let's just print the candidates out and see what we got. I candidates. L, oops, L is I, and R is R sub I. Hey, bear with me as I debug this here real quick. Let's see what happens. Let's just do the simple example. How about 1, 1? Actually, for 1, 1, I can let's just do this, right? Copy. Let's just print these things out. Right, just print out a list of integers. Do that for R as well. L and R. So L, R is our candidates as we go. Okay. 1, 1. L should not ever equal anything. How is the L is equal to anything at all? Left, oops, I want a 1 there and a 0 here. Right, we count the zeros to the left and 1 to the right. Okay. Right, 0, it's right. 1, 2, 3. That doesn't, I don't know, is that right? No, we're doing 1 too many. Don't want to go all the way to there. 1, 1, it should be 0 is the best score, right? 0 is the best score. Okay. Yeah, okay, that's the right answer. Okay, so, all right, I think I might have fixed it. Let's see what happens here. Nope. L are index 1, the best is 2 is what I'm saying, which is not correct. How many zeros are there to the left of these things? There's zeros to the left. Left does not look correct. Because zeros should count. What the heck? Is that XOR precedent? Let's see. Should be 3. Okay, so this is not quite right. Still off by a bit. All right, let's just focus on this first one. How about 0, 0, 1, 0. Answer is 2, 0, 1, 2. Should be 4, 0, 1, 2, 3, and then 4 is that last one. Left and right. Okay, so we're putting a 1 there, we're putting a 0 here. All right, 1 to the front. So that doesn't count here, but it should count here. There should be a 1, right? Because that thing, a sub I minus 1, XOR 1. Oh, wait, no, that is 0. Okay, so that doesn't count. Okay, but this one does count. Okay, so that's right. So 1 there to the left. Or there's a 0 to the left of that. Right? I think that's right. There's 0 to the left of this thing. Yeah, so it's 1. There, let's just grab these real quick. These are my expected calculations, right? It's 1, 0, 1, 1, 1, 2, 1, 2, 0, 3, 0. Okay, so these are the correct calculations. These are right. I'm not going to the end there. So, okay, so that is not right then. I'm not going to the end. Go to here and it should work. 2 and 4. Right, okay. And let's try this one next. 0, 0, 0, 0. Should be 3, so that's right. And then 1, 1 should be 0. Sometimes I feel like I fix this as I'm like debugging it, and then I'm like, well, I don't even know what I changed really. It's too early, not enough coffee, I guess. All right, this looks legit. Put my debug stuff and then submit it. Man, it sure is taking a while. I do expect it. Okay, yeah, I was gonna expect it to work. Okay, so that's legit. Let's do this. I can definitely use some more practice on these kind of things. Oh, man, I cannot type Python. Oh. Hold on, let me go grab that code and then I'll do this in JavaScript and Kotlin too. hopefully I can increase my coding abilities. I don't have to do so much debugging. It's good practice. Alrighty, let's try this again in the JavaScript. Hopefully it's a little bit faster. 6:17 is when I'll start. Okay, let's give this a shot again. Excuse me. 0. And then M will be our map. Check out our best, return, and not get best. Okay, and then A is going to equal 1 there. Cat. Or actually, I know what we can do is just do this spread operator. Should be fine. Okay, let in length. And then let L equal array in. That one with zeros, and do the same thing for R. Okay. -1 to n I will build it upon itself. I-1, a sub I-1 size non-inclusive. Oh, by the way, what? I remember there was, yeah, this thing, XOR. I'm gonna try this. Maybe that was the fix. Is this putting the XOR in parentheses? So what happens if I don't do this? Okay, so XOR does not have precedence over the plus. So that was my mess right here. All right, so this part gets a gold star, these parentheses, operator precedence. Plus over XOR, right? Okay, that's good to know. It's like, felt like magic when I solved that thing the first time. Okay, that's good to remember. All right, I did remember that. So put the parentheses here. Alrighty, and then do the same thing, build up the recurrence relation for R from the left to the right, or right to the left. R sub I, 1 to the right, plus A sub I. Alrighty, and then formulate our best. Candidate is L sub I plus R sub I. If best doesn't equal the candidate, set the best equal the candidate, and then if m dot has best, then m dot set best to a new array, and then m dot get best dot push I -1. We offset the index by 1. Okay, that looks legit. Okay, so take a while. But if this is accepted, that's cool. It'll be about 3 minutes. Cool. Okay, about 3 minutes. Yeah, that's pretty decent coding accuracy. I'm getting there. Alrighty, and then let's do the Kotlin real quick. Okay, I'm gonna start this one at 6:21. See how long this guy takes. Okay, so in Kotlin, we want to push it to the left and the right. We'll have to use mutable list, right? So let's do this. A equals a dot to mutable list, and then a dot add at index 0, the value 1, a dot add a dot last index 0. And let's do this. Print a.join to string. Just print a real quick, and then let's return list of just to get that to compile. Okay, cool. So I pinned a 1 to the left and a 0 to the right. That's legit. I wanted to print that out because I'm still kind of new at Kotlin. Okay, and then we also want to have, let's see, var m equals immutable map integer to mutable list of integers. Add on to return m dot best dot to list. Right? Transform that mutable list into a list. Keep track of best. Oh, that's 0. Okay, and then calculate ln based on a into array of n size n and 0. R is also an integer array size n initialized to 0. Okay, and then let's fill in ln. So for I and 1 till n, I equals also I minus 1 plus, don't forget those parens for operator preference. Flip that bit, and for I and n minus 2 down to 0, do the same thing for R, build it upon itself. So one place of I, and then for I and 1 until n, candidate is L sub I plus R sub I. Let's see if best let's make the candidate, then best equals the candidate, and if m doesn't contain best, and m sub best is a new mutable list of integers, m sub best, add I minus 1, we offset the index by 1. Okay, let's see what happens. Atlas, uh-oh, that's not right. 2, 3, or 2, 4, 3, and the last one should be 0, not 2. Ones and zeros. XOR 1. Okay, let's print this out and see what happened, what went wrong. Actually, maybe I'll look at the code here real quick and try to tell what went wrong. 0. Add a 1 to the left, 0 to the right, sentinel values. XOR 1, flip the bit. That's right. That's 1 to n non-inclusive. Doesn't include that. -1. Yeah, I don't know. Let's do this. Print L join to string. And then let's do the same thing for join. Join to string. Let's do the same thing for R. L should all be zeros. R should be. Oh, is that a 1? What is best then? Best should be 2, right? Best 2? Best is 1? Oh, there you go. That's why. 0 to n. Right? Answer is -1. 2. Oh, let's see. Hold on. Worship. I is inclusive for R. I. Worship I. It should be a 1, right? Hold on. A equals 1, 1, and then I append a 1 here and a 0 there. So L equals 0, 0, 0. It should be all zeros, right? Why is there a 1 at the end? Hold on. Here. A dot join string. Just join A. It should be 0, 1, 1. Wait, 1, 1, 1, 0, right? Not right. Add 0. Okay, so adding it is not right. Okay, so Kotlin. Add to list. Let's do this. Go to this guy. Docs. Search for add for immutable lists, right? Immutable list add. Add all. I want to add it a specific index. Element, index, element. This is the one I thought I was using. Index. Like, what the heck? Oops, hold on. Where am I? Okay, this one. Wait, 0. I'm trying to add a 1 to the beginning. Two mutable lists. A dot. All right, A dot first index. Does that work? No. I want to add it at the first index. I want to. It should be. Yeah, this is what A should be. 1110. What the heck? How are you not 1110? Push a 1 here to the left and a 0 to the right. What the heck is this? Like a 0 to the right. What the heck? Mutable list, add, index. The heck, man. How are you not adding? The heck? Here. Print it twice. To 111. Okay, that is correct. Last index. Okay, so that's why. Okay, last index is where you insert it before. Okay. Or just add it at the end. All right, just add 0. Keep it easy on myself, right? Okay, and then I do want from 1 to n. Right, it's just 0 because 0 is not inclusive for left. Okay, so that is right. Okay, and then do my test cases. Everything should be legit. All right, 2, 4, 3, and 0. Okay, that looks right. Okay. Signal values. These print statements, and we're in business, I think. Seems cool. Check it along. Okay. Still working. Yay. Okay. It's accepted. Oh, this one took a while. 6:32. Like 11 minutes. I had to debug that. Had to debug this part. Wasn't adding onto the mutable list at the right part. Okay, that's a decent solution. Alrighty, let's post this and we'll get back to that other question. See how much time I have left. Use a map to store each candidate, each ith, right? And track the best. List of indices. Right, okay, so use a mapm to store each ith candidate score, track the best score to return a list of indices, which the best score, with the best score, list of indices with the best score as the answer. To make thing, okay, also, and I guess to simplify the code, we can append signal values onto the input array A. A equals 1, A 0. And to avoid TLA, we calculate the prefix sums from left to right and from right to left. To perform O of 1 calculations. For each ith. I think that works, right? Use a mapm to store each ith candidate score. Yep, that looks legit. All right, a few solutions. If I can type. Solutions. All right. Kotlin, JavaScript. Hey, it seems like a decent solution. That's okay. Alrighty, that's that. And then already, yeah, it's the same thing. Okay. How much time do I have left? Holy cow, I only have 3 minutes left in the contest. That took a long time. Well, I got 2, so that's cool. I still need to figure out how to solve this one, and I haven't looked at this one yet. So cool. Yeah, thanks for watching. Lots of upsolving to do. Maybe I'll try to upsolve this one and then code it in another video. And then Q4 is always an elusive creature. I'll have to dedicate a session just to that one, probably upsolve it. Well, yeah, I don't think I'm going to solve this one in 3 minutes, but I do believe this one is DP. I believe I can use the previous calculations to derive the next one as the window slides, or do maybe some kind of smarter pre-calculations. So as the window slides, it might take into account the power shift. There's some trickery going on this one. Kind of close to getting 3, but not quite there. Yeah, this is a super naive solution of n squared, right? It is correct though. Super naive solution, naive solution, but it's correct and a good start. I have a lot of room for improvement. Yeah, it's contests like this where I get like 2 and I'm struggling on 3. It's a good reminder. I have a lot of work to do still. A lot of room for improvement. It'll keep me humble. Keep me hungry. Okay, well, anyhow, I got 1 minute 52 seconds. Not gonna solve this one in time. I guess I can take a peek at this one, see what's going on here. Group of strings, you're going 0 index array, lowercase. No letter occurs more than once in any of the strings. They're all unique characters. They're said to be connected. The set of characters S2 can be obtained from those by one of the following operations: adding exactly 1 character, deleting exactly 1 character, replacing 1. Okay. The arrayed words can be divided into 1 or more non-intersecting groups. It is connected to at least 1 other string of the group. Is the only string present in the group. Non-intersecting groups. To at least 1 other. Okay. Words of 0 can be obtained by words of 1 by replacing one of those. They're off by 1. Oh, okay, this is cool. Actually, yeah, this one is way easier than Q3, I think. This one is way easier. I don't know why I'm like, I feel like I'm in Q3, right? I'm totally psyched out. PSY psyched out by Q4, I think. Like it's a self-fulfilling prophecy that it is hard, because this is pretty simple, right? Use a map to count each word. Like basically, since alpha from A to Z only occurs once, it's pretty simple to come up with the hash, right? Right. The hash basically corresponds to 32-bit integer using 0 to 25 for A to Z inclusive, right? And then we just do union find, union find for connected components and linear time. So this one, it should be a fun one. I don't know why I didn't just skip to this one. I'm pretty sure, yeah, if this is a contest, I would have wasted a whole bunch of time on Q3, and then Q4 is just like low-hanging fruit. So let me end this video because I like to try to end them promptly at 1.5 hours, and then I'm gonna come back. I'm gonna do this Q4 and show who's boss. All right, thanks for watching. Catch you next time.